My name's Irene, and I'm the coordinator of undergraduate recruiting, research, and placement for our physics department. So if there's any high schoolers in the audience who have questions about what it's like to be a physics major, I'm happy to answer those questions. But otherwise, welcome everybody to our lecture today. We've got Professor Brian DeMarco, and I'll introduce him in a second. But in general, our lecture series is a public outreach event, so open to everybody who's interested in learning about all the different physics that we do in the department. Also, if you want to learn about different kinds of physics, thinking about being a physics major, this is a great place for you too. If you would like to sign up for emails, we've got an email sign up upstairs and a QR code that you can scan if you want to. And I think that's all of my announcements. Oh, actually, next Saturday of Physics will be on October 26th, and we'll have Professor Kirk Barrow, who is an astronomy professor, and he'll talk about his work in that field too. So, without further ado, I will introduce our speaker today, Professor Brian DeMarco. Professor Brian DeMarco is a professor of physics here at the University of Illinois in Urbana-Champaign. His research team uses atoms and light to expand the frontier of quantum science, computing, and networking. Professor DeMarco leads the National Science Foundation Quantum Leap Challenge Institute for Hybrid Architectures and Networks. This multi-institutional Midwest center works to establish a new paradigm of quantum computing, which involves nodes of different qubit platforms connected by network links. Professor DeMarco is also the director of IQuest, which is our Illinois Quantum Information Science and Technology Center, which supports the portfolio of quantum research at UIUC. Professor DeMarco is also an associate director and the chief technology officer for the new Illinois Quantum and Microelectronics Park, which is very cool. A fun fact that he wanted to share today is that he has a son who is a freshman here at UIUC in mechanical engineering, so not in physics, unfortunately. We'll have to be okay with that. And he actually takes Physics 211, which is our introduction course in physics mechanics, in this very room, which is very cool. So please join me in welcoming Professor Brian DeMarco.
Okay, so can everyone hear me all right? Good. So I'm so happy to be here with you this morning to talk about quantum computing. What I wanted to do today is to give sort of a big picture of quantum computing. What is it good for, and what's happening at the university and at the state, because our state, the state of Illinois, has emerged as a global powerhouse in this area, and many exciting things are going on. Please interrupt at any time with a question. I'd be very glad if this turned into a conversation. And we can also take questions at the end if you want to wait. But just interrupt. It's no problem at all. All right, so Irene, thank you for the introduction. Indeed, I seem to have acquired too many full-time jobs at the moment. So I'll tell you a bit about that last one, the new IQMP, which is a new 130-acre tech park on the south side of Chicago at the end of this talk. And it's a very exciting new opportunity that I hope creates a wide range of jobs for a lot of our students in the high-tech sector to stay in the state after they get their degrees here. Okay, so let's see. Great. So what I wanted to do as a kind of intro to quantum computing was to talk a bit about the 20th century revolution, which is just computing. I see, I need to be closer. I can make that work, or not. Okay, there we go. I'll just stand here. So that revolution started with the creation of semiconductor digital bits. What are digital bits? Well, they start with quantum electrons in a semiconductor like silicon. And then we turn them into transistors. And this is one of the smallest transistors that we have today. And once they're a transistor, all that quantum physics is hidden. And a transistor just acts like an on-off switch. That's it. So all the quantum physics we hide. And that's how we make conventional computing. All the things in the computer, like your laptop, all the various processors in my phone, memory, that's how we make all of that. And what that allows us to do, what computing really is digital information processing, where we can take a stream of those bits, ones and zeros, transform them according to some rules, that's a computer program, into some kind of output. Input, computer program, output. And what's inside that computer program eventually is all the way down at the transistor level is a bunch of circuits, electrical circuits that processes that information. So when you type on a keyboard, there's some bits, there's some rules in the computer or program that turns that onto words on a screen. Now that seems so simple, but it's an incredibly powerful idea because it's a completely transformed society because you can really digitize almost anything into ones and zeros. So that's what's made searching the world of information at our fingertips. It's made that possible. It's made climate prediction possible, much more accurate than we ever had before. The last 30 years, the ability to apply computing to climate prediction has really transformed all kinds of industries, including flights. I don't know if you've noticed this, but there's a lot less turbulence. You experience a lot less turbulence in flights than you used to, and that's because we've gotten much better at weather modeling. You can digitize music, right? So you can carry music around. I can play music on my phone because it can be digitized. And even art can be digitized, right? 30 years ago, if I wanted to see this painting, I had to go to Paris, and I did, and it was amazing. But now you can see this painting on high resolution anywhere in the world. So this has really completely transformed society. However, there's something that we often don't talk about with computing. You know, with computing, it seems like every year there's more and more computing power around us. You'll just pop more computers on the cloud, and we can compute more. And there's some subtlety there that I wanted to mention. Some problems for computers are kind of easy. Let me tell you what that means. And that means that, like, if I have a problem of a certain size, and I'll give some examples, and I double the size of that problem I want to compute, it takes about double the resource, double the memory, or double the time to do that. That's what easy is for computing. So things like that are phone contacts. Like if I double the number of contacts in my phone, you know you can kind of do that. You don't have to get a much bigger phone. That's because that's an easy problem. Hospital patient records is also like being able to search and store hospital patient records is also like that. That just takes a bigger computer to do that. But you know, we're not running out of computing to handle patient records. Tax records, even bigger. But again, we have, you know, cloud computing can take care of that, and it's not like we're running out of the ability to process their taxes every year. So that's what's easy for a computer, and that's why you see a lot of these problems all around you, very common problems. And that's why one reason it seems like there's always more and more computing to be had. But there are some problems that are really hard for supercomputers. I'm going to give you one example that seems esoteric, but actually this is a really important example. And that example is exactly simulating molecules. And exactly simulating molecules, when you do that, when the problem doubles, it requires not double the resources, but many, many, many more resources. So as problems we want to solve about simulating molecules, as they grow in size, we need exponentially more computer time or computer size to process them. So let me give you an example of this. So the one problem that you can do is calculate exactly everything about hydrogen, kind of the simplest molecule, even just one atom. I can do that. Actually, I can do that on my phone these days. I should have put a picture of a phone there. That I can compute on my phone. No big deal. I can compute everything about it. Slightly more complex molecules, like I forget what this is. I should have gotten in my head which one this is or put it in the PowerPoint notes. This is some molecule. This might be caffeine. It's not caffeine. Anyways, as the molecule gets bigger, I can deploy a supercomputer like the supercomputers we have around the campus or at Argonne National Lab, and I can compute almost everything about that molecule. But once I get up to pretty complicated molecules and things we really care about, you know, what you see here is a picture of a high-temperature superconductor, and if we have time, we'll get one out and play with it. High-temperature superconductor, very, very important material made up of molecules. The other thing you see here is a photosynthetic complex, very important. Energy harvesting is very important. We would love to be able to exactly simulate superconductors so that we can make them better, or our energy harvesting molecules so we could optimize or maybe optimize solar collection of energy. But there's a problem. These materials have many more than 300 electrons in them, right? They have millions of billions of electrons in them, in the most basic unit of them. And the trouble is, once you get up to 300 electrons, it would take more bits than there are protons in the universe to even store all the information you need to simulate that. So no supercomputer will ever do this, because once you get to 300 electrons, we can't exactly compute it. We never will. We can't even store the information we need in the whole universe. Game over. Okay, so these are problems that a lot of industries care about, a lot of scientists care about, and we will never be able to exactly simulate them using any supercomputer we can ever build. Okay, so that's a hard truth, and it's one that in my research I confront all the time. Is no one will ever calculate it. But there was a 20th century discovery, and that's the story I want to tell you a bit about today, which is that if you can make a quantum computer, and I'll tell you what is a quantum computer at this high level, and I'll dig into examples of quantum computers. If I can make a computer out of quantum bits, and I'll say what those are, it could compute certain tasks exponentially faster. So that's good. If something's exponentially harder, but you can compute it exponentially faster, then you can get it done. The first example, so this is the idea of it. The idea, and sometimes people think, oh, am I going to have a quantum iPhone at some point? And that's not what a quantum computer is. A quantum computer is something that you take a regular computer and you add a quantum processing unit to it as like an accelerator. You should think about that like a GPU. Does anybody know what GPUs are? Yeah, my first GPU, I remember it was from a company that's gone out of business, 3DFX. I got it and put it in my computer in a slot, and it made it play video games better. What are GPUs used for now? Does anybody? AI, yeah, for training large language models, right? Turns out they were really useful. And keep that in mind. It started off for gaming, turned into something very useful. You should think about it like that. A quantum computer is something you add to a regular computer. Actually, we probably will add it to a supercomputer so that the supercomputer can do those really hard problems. And, oops, let me go piece by piece. So I'm showing what kind of a diagram of what quantum hardware looks like here, where there are qubits or quantum bits that are an input, and that quantum computer, quantum processing unit, transforms them according to some rules to an output. So it's really not that much different than a regular computer. There's a quantum logic circuit in there that does that. That's the quantum program or the quantum algorithm. You can think of it that way. It's not really any different at that level. And that first program, the first quantum program that we found was something called Shor. It was Peter Shor came up with it. We call it Shor's factoring algorithm. And it's an algorithm that allows us to factor numbers, like factoring is like 15 equals 5 times 3 times 1, much, much faster than a regular supercomputer. Does anyone know why that actually caught everybody's attention right away? Encryption. Yeah, can you say more?
We use very large numbers that are 2 prime numbers multiplied by each other to do encryption. And the only way that you can receive encrypted data is by knowing which your 2 prime numbers are, which your computers know. It's what all 45 or something.
Yeah, that's right. So the fact that factoring really big numbers, you're exactly right, is really hard, is how I can order something from Amazon on my phone, and my credit card information can be transmitted to them, and it's protected. So if you had a quantum computer that could catch that information and decrypt it, that seems kind of important. So this caught everybody's attention right away. This breaks our modern encryption systems that we use for transmitting information securely. Okay, that caught everybody's attention and really spun up efforts all around the world to build a quantum computer. And I'll tell you, again, more about what that is. Remember, you can interrupt and ask questions if you want. Okay, so now we're in the middle of a 21st century quantum revolution, right? 20th century computing, 21st century quantum computing, where there are these quantum bits, or qubits, and there's a big difference right now compared to computing with quantum computing. So people unlike silicon CMOS, right, which is the basic, there's a uniform kind of bit in my phone and a laptop everywhere. We standardized it. We can mass produce it. Right now, we don't know which kind of quantum bit will actually work to get us to a good enough quantum computer that it's useful. So people are trying to work with all different kinds of quantum bits and develop that technology right now. That includes photons, or particles of light, atoms, both neutral atoms and atoms that have been singly ionized. So you rip an electron off. Superconducting circuits, so that's another kind of qubit. and material defects. So these are color centers in various materials, and you may be familiar with color centers in diamond. You can buy diamonds that have slightly different colors, and sapphire can have all different kinds of colors. That's because there's defects in there. That means that an atom has been replaced by something like a metal atom, and it gives it that color. And these are all actively being developed here at UIUC and throughout the state, in fact. And there are companies that also are trying to use all these different kinds of qubits to make a big quantum computer. And so it's now like almost a global race, and I'll tell you a bit why and what that looks like, to get to the point where we know how to take these types of materials and atoms and turn them into a big quantum computer. Okay. So how is quantum different? So the conceit is this. Remember how I told you when we figured out how to make a computer, we started with quantum electrons and a semiconductor, and then we hid all the quantum about them, and we just turned them into an on-off switch? The whole idea of a quantum computer is now you want that quantum physics to be completely present. That is the thing you're going to use to do computing. No more on-off switch. Something more complicated is going to happen. And we can talk about that. So first of all, how is quantum different? Qubits are not digital, and that makes them very fragile. So with digital logic, like in a regular computer, the bits can be 0 or 1. And actually, the way that works is there's an electrical signal. And if the electrical signal is above a threshold, you call it a 1. And if it's below that threshold, you call it a 0. And that actually makes the digital logic very robust, right? The fact that you can put that threshold in here, and it can stand a little noise. Like, if the electrical signal is kind of like changing a little bit or changing a little bit, it doesn't really matter. It will be a 1 even if there's some electrical noise, or a 0 or even if there's electrical noise, and it makes it very robust against that. A qubit is different. A qubit can be 1 or 0 or anywhere in between. What does that mean? So the way that we think about a qubit is that it points in a direction on a sphere. If it's down in this picture, if it's pointing down, it's 1. If it's pointing up, it's 0. But it can be 0 and 1 if it points horizontally, for example, and anywhere in between. And in fact, it is something, oops, what's the next thing? It is something that, is very delicate. It's what we call quantum superposition, that it can be 0 and 1. And it makes it much harder to control, right? Because if it can point anywhere in that sphere, and we really care for the quantum program that it points right there, if there's a little bit of noise, then it's pointing in the wrong direction, and it's the wrong quantum bit, the wrong number. So we've lost that thresholding between 0 or 1, that robustness against noise. Now any little bit of noise messes up our quantum program. And so that means that it's much more fragile, and that's why quantum computing is so hard, in fact, is we have to protect the quantum computers from the environment. We have to surround them in vacuum and ultra cold, and I'll tell you about that, to protect it against all the noise around it. And it's even worse than that. We have to protect it from all the noise around it, but we still have to be able to send signals in to control it and read it out. Those two things are in tension. That's what makes it really hard. For me, that's what makes working on them really fun. I like hard things, but it's hard. And I'll show you what some of these experiments look like. The other thing that's different about quantum is something called quantum entanglement. So in a regular digital logic, if you have a stream of 0s and 1s, whatever happens to one of them doesn't depend on all the other ones, right? I can send a 0 or a 1 through my program. It's just going to do its thing. I can send a whole bunch of 0 or 1s in, and they're all going to do their thing in that program and give me an output. In a quantum computer, if I have a bunch of qubits, I can do something called entangle them. And we can get into what that really means. It's, I would say, hard to explain, which means there's still a lot for physicists to learn about it. We can entangle them, which means that the quantum states completely depend on each other. For example, and then they're not independent anymore. So for example, if I have 2 qubits that are entangled and they go through this quantum program and come out the other side, it could be a situation where if they go through and I find this one's a 0, this one's always a 0. If this one's a 1, this one's always a 1. And I could not determine before they went through the program, and I read out the output, what they were. And it turns out that this is very useful. These two things, superposition and entanglement, is what gives quantum computing extra power. And I think we're still even discovering why that is, and how to use it, and how to use that as a resource to do better computing. So where's my friend who had a question? I said you should ask her this question. Oh, you have, well, okay, well, hold on. This is great. What's your question? If, I think you're asking a really good question. Is that an owl? That's an awesome owl. Does your owl have a name? It's a movie I don't know because my kid is all grown up now. Cool. Okay, I think you just put your finger on something really important. What if we have these qubits that are quantum entangled, and it's we want it to be always that this one's always 0, this one's always 0, this one's always 1, this one's always 1. What if something goes wrong and noise gets in there, and it was supposed to be 0, but this one turns out to be 1? That's an error in the program, and that's bad. And that's why this stuff is so hard, actually. That's what noise can do to quantum entanglement and get in there. Okay, so were you going to ask your question? Later. Okay. All right. Yes?
You've gone from change dimensions here between bits and qubits, and I'm trying to understand how change dimension relates to quantum.
Okay, you're exactly right. There's some beautiful math behind all of this, and you said something that's really important. You said there's a change in dimension. And so remember how I said that if I have 300 electrons, that I need more bits than there are in the universe, protons in the universe to store that? Actually, if you have 300 electrons to store everything about their quantum state, you only need about 300 qubits. Because a qubit can actually hold more information in some sense, because it has a higher dimension. And there's a very specific mathematical way to say that, but you actually intuited something that's really important here. Yes?
Sorry if this doesn't make sense. You said quantum processors are more akin to the GPU.
Mm-hmm.
You plug into a regular computer. If qubits need to be near absolute 0, would it ever be possible to have something like that in your pocket?
Okay, great question. The question is, I said things need to be near absolute 0, and I'll show you something that's, could I ever have it in my pocket? For that kind of technology, no, you can't have it in your pocket. I'll show you what it looks like. But that's one reason people are exploring things like these material defects. There may be a way to get qubits that can work at room temperature, and then maybe it could be used for that or for other applications. So far, we don't have, you'll see you need like vacuum and all kinds of things right now for the technologies we have. It could be that there's a future where we find a room temperature qubit that could work. And there are a lot of people trying to think that through and figure that out. The computers we have now, I'll show you pictures of them, they will not fit in your pocket. And that's actually where we're building a tech park, is because we need 130 acres to put a bunch of computers there. Hold your question. I would say they're not in the lead, but it's complicated. And I'll get to that in a minute. Yeah, so here's a practical thing. So I said, let's do this by a comparison. So the question is, how is it that it stores more information? I don't want to start writing down math. Nobody wants that. Let me say this. So I can give you a fact and then try to help you with it. So it just turns out that if, for example, if you need, okay, I'll give you some numbers, and it may not mean a whole lot. So if you have 300 electrons and they can't even move around, and you want to store all the information about them, you need to simulate them. You need 2 raised to the power of 300 numbers. That's the same as 10 to the 90. 10 to the 90 is a really big number, and that's more than there are protons in the universe. And that's because quantum mechanics is complicated, and it requires storing a lot of numbers to calculate things. On the other hand, if you have 300 electrons in the same situation, they can't move, but they still have quantum states you want to store, you only need about 300 qubits to store everything about them that you need to compute. That's kind of a fact. And so that that's signaling to you that they can kind of store more information, right? And the reason for that is there's a lot of information in where an arrow points on the surface of a sphere. There's a lot more, right? Because just think, if I have to keep track of it, somehow I've got to keep track of a lot more information than just 0 or 1. And that's what I was trying to say. Yes? Yeah, and I'll show you this actually. For example, IBM has put quantum computers on the cloud now. And so it costs, IBM's pricing model, I think, is a little out of whack. It's very expensive. But if you pay them enough money, you can, through a phone, even your phone, you can interface to them. They don't have to be, they can be out in a data farm. That's absolutely true. And I'll get a little bit more into that. Go for it. Okay, so the question is, this is something that really, really bothered Einstein, which was if I say I take two qubits and I entangle their quantum states and I pull them really far away from each other, and let's say I'm in a situation where what entanglement means is I can't say this qubit is 0, 1 or this qubit's 0, 1 until someone looks. And let's say as soon as you look, this one is 1 and this one is always 1. That happens as far as we understand it simultaneously. However, that doesn't allow you to transmit any information. And that means that you don't break the speed of light because it doesn't allow you to transmit information from party A to party B. No, that happens. That actually happens. You can change this one and this one simultaneously changes. There's a subtlety there that it doesn't actually allow you to transmit information from one to the other. Because when you go measure, the process of measurement is random. You know, I'm going to find this one. And so there's some subtlety there. And actually, we shouldn't get too diverted into this. And that you can't transmit information faster than the speed of light using entanglement. And that's what keeps causality, like the fact, cause and effect, okay. So that super bothered Einstein that this was true, and then we learned a lot after the 1920s, 1930s about this, and that's what keeps it all okay, is that you can't transmit information. But I feel I don't want to get too diverted into this because I want to show you what quantum computers really are. How about one question and then another one? Go ahead. So that is actually unrelated. We believe that the speed of light is the same everywhere in the universe, and the speed of light this way, an exact reverse path is the same. That's unrelated. We believe that to be true, but that's unrelated to this, it turns out. Yes? That's a great question. How do you encode it into 300 quantum qubits? And actually, it's the reason I use this example is it's really simple. I actually just I make the qubits look just like the electrons because they're both quantum particles. That's the trick of quantum computing. Now I've raised up the quantum physics. I haven't hidden it anymore, and that means that because it's right there in front of us, and qubits are quantum, and the quantum physics is the fact that this is superposition entanglement. That is a quantum physics. I can make them look just like electrons, and so I just need about 300 of them because they can do exactly what the electrons are doing. And I can, by sending signals in, I can set up them to look exactly the same. And I'll show you some examples of what it looks like. Okay, these are great questions. I want to show you some examples of what quantum computers look like. I think this will be is important because I think it's good to see what they are. Great questions. Let's come back around at the end, and I can stick around and chat with everybody about this. So I want to say a little bit about what is this 21st century quantum revolution that we're in the middle of now. What do they look like? Who's making quantum computers? Someone asked, is the superconducting circuits the bleeding edge? The answer is no. Yes, and others are equivalent and different. So we're in this middle of this quantum revolution now where all this quantum information science, these qubits, people are using them to try to make quantum computers or these quantum processing units. Actually, it turns out people are also trying to use them to make quantum networks and also quantum sensors that allow us to sense the environment around us better. These are huge activities all around the world, and I wanted to make sure you knew that there's sort of 3 buckets of things that qubits are used for. I'm just going to now tell you a bit about what do quantum computers look like and what's happening. All right, but there are people, including myself, who also work on quantum networks around here and on quantum sensors. I don't work on quantum sensing, but for example, I have a colleague, Mikhail, over in chemistry, who's working on trying to use defects in diamond to be able to sense traumatic brain injury better in a patient. And so there's very important applications of that. And one reason I'm not talking about networks and sensors is I know a lot less about them. So I don't want to get myself in trouble. Okay. All right, so let's talk about what the state of the art is in quantum computing. As I mentioned, there's no winner yet for qubit platform. We don't know which one's going to work, so I want to tell you about 2 of the leaders. Happens to be we have people working on them here. One of the leaders is these superconducting digital quantum computers. This is a picture of the guts of one. I think this is at Google, this particular image. What you're seeing there is the inside of what's called a dilution refrigerator. It is a kind of refrigerator. It cools materials to just 10,000ths of a degree above absolute 0 temperature. And so this is the inside of it. If it was all bottled up, you'd just see a can around it to shield it from the environment. And it uses helium to cool to those ultra low temperatures. You can see there's a whole bunch of wires there and racks of wires. Those are wires that carry in electrical signals in and out to the qubits that sit at the very bottom of that fridge. In order to run that program, to send inputs as qubits, to run the program, and then to read it out. And each one of those is what's called a coaxial cable. Those of us old enough to remember cable television, that's the kind of thing that came into your house that was like the cable. These are just really fancy ones. And the signals occur at much higher frequencies, at gigahertz frequencies, rather than radio frequency. And this is a state-of-the-art machine. You can see it takes racks and racks of electronics to run this. This is not something you're going to get in your pocket. This is something which is going to go in a data center. And actually, this is one of the most advanced processors that IBM's deployed. It's called the Osprey. It has 433 qubits. I want to show you IBM System 2. I was at IBM and I saw this being constructed. To give you a scale, that's about, those cabinets there are about twice my height, more or less. And inside that are 3 IBM Heron quantum processing units. Each one has 133 qubits on it. So that is something that you have to be a very special person to access that machine. You can't just buy access. But that is a machine that's out there. It runs quantum programs, and people are using it right now to do that, to do quantum computing. And we also do this here. So here's a friend, and you can see when I took this picture, this was in the middle of COVID. This is over in the engineering sciences building. This is a dilution refrigerator that we have in what we call the IQUIS testbed. You can see at the very bottom of that, there's some cans. They are cans made out of aluminum. And it's the shielding. So there's layers and layers of shielding here. This is open, so it's warm. It gets all closed up, gets cold. And what I've done there is zoomed into a picture of a superconducting qubit that was made here at the University of Illinois. So I am going to use the pointer, and I'll tell you what I'm pointing at. So right here, so that qubit lives inside a holder that allows signals to come in and out. So that's this top and bottom aluminum plate that these plates get screwed together, and one of those cables comes in on this connector here. And if you zoom in, there's a micrograph here of what's called a transmon qubit that we made. So I didn't make. So sorry, this team of students made this transmon qubit. And what it is, what you're seeing there is very beautiful sapphire, that's the rectangle there. Deposited on that is layers of aluminum and aluminum oxide. And that shows what's called a Josephson junction right in the middle of there. It's a sandwich of aluminum and aluminum oxide. The green is layers of aluminum and aluminum oxide. That little qubit lives right in the middle there. It's about 100 nanometers or 100 billionths of a meter in dimension. So that's what it is. That's what it looks like. And aluminum is a superconductor at very low temperature. It's made out of aluminum. That's what it really is. So one of the reasons this is a technology that a lot of people are excited about, and I'm going to do something here and I'll show you something just for fun. One of the reasons this is a technology people are excited about is it's kind of manufacturable. So you can go ahead, you can manufacture it, you can go into a foundry or a fab, you can get this magical sapphire and a magical aluminum evaporator, and you can make highly complex circuits and make hundreds or thousands of qubits on that piece of sapphire out of superconductor. And that's one reason people like it. One reason it's a challenge is that we don't understand everything about the materials inside that superconductor. So there's things happening there. We don't know everything about the physics and the science of it and the material science. And that's what makes that particular type of qubit hard. Superconductors are fun. I've got a piece of high temperature superconductor here. High temperature superconductors are ceramic. It's not as manufacturable as aluminum. I think we all know you can machine aluminum. I'm showing you machined aluminum parts. Ceramics are harder to work with. And this high temperature superconductor superconducts at liquid nitrogen temperatures, which is 77 Kelvin. So I've poured some liquid nitrogen in there. And I'm following my procedure. I've got someone from the Division of Research Safety there, so I'm making sure he sees I'm being very careful. And so I'm going to submerge this in liquid nitrogen. You're just seeing all the liquid nitrogen boiling off because this is hot and it's got to get cold. And one of the things that's true about superconductors is they conduct electricity without resistance. That is linked to something else that's very important called the Meissner effect, named after a person, Meissner, who figured it out. Meissner effect tells you that a superconductor is also a perfect diamagnet. That means that it expels all magnetic field from it. And so what I've got here is a track, and there's a whole bunch of magnets on this track. And this is the source of magnetic levitation. In fact, water is weakly diamagnetic, so you can levitate things made out of water. You just require much bigger magnets than the magnet that I've got here. This really does take a while to get cold. All right, let's see if it's cold enough. I think so. And I'm wearing gloves because liquid nitrogen is cold, and it, just like something very hot, it'll basically burn you. So let's see if I've got, oh yeah, there you can see. It just levitates and goes around the track because it expels all the magnetic field from it. Oops, well, I'm not very good at this. Anyways. Uh-oh. Yeah, I didn't get it actually quite cold enough, but there you go. There you can see it's kind of levitating. Okay, pretty neat, right? Superconductors are really neat. Now I'm realizing I didn't ask how I'm supposed to dispose of all that liquid nitrogen, so I'll figure that out later. Yeah, sometimes you do things you're like, oh, I forgot about that part. Anyways, that's a superconductor. It's a high temperature superconductor, but we can't use those for quantum computers yet because they're just not manufacturable enough. Okay, so that's a leading technology. It's a real thing. IBM is one of the companies that makes actual quantum computers out of superconductors. Irene, how are we on time? 15 minutes? Okay, cool. Okay, another, and this is something we work on here, and we don't work on making big quantum computers here. We do the science, which is 10 years out in front of a company like IBM that is super risky, that they could never justify to their investors. And we actually partner with IBM on trying to figure out some of the science questions they have that they're going to run into in about a decade. That's the role of the universities, and it's a very important role we can play to help industry move forward. Another quantum computer that's a state of the art are trapped atomic ions. So okay, so I forgot to say something here. The qubit, what actually makes the sort of 0, 1 in this is electrical current running through a circuit of that superconductor. And you can imagine in certain cases, it's like the superposition is current running around in one direction and around the other direction at the same time, which seems kind of weird, but that can make the qubit. This is a picture of a trapped ion quantum computer, and I'm going to show you one and explain a little bit more that I'm making here. This is a picture of a device. It's about this big, about a centimeter in dimension. And this is from a company called Quantinuum. This is their H2 device, where they have fewer qubits. There are 32 qubits that they can work with on this device. And hold the questions for a minute, and I'll show you what that really is like. But they're much higher quality than the IBM qubits. And so where the IBM qubits are noisier, they have fewer higher quality qubits here. And so the Quantinuum machine can do some things the IBM machine can't do, and the IBM machine can do some things the Quantinuum machine can't do. I have a lab and a research group that's building these kinds of systems here, and I can show you a little bit more about what these are. This is our chip, and you can see the dimension. This is my student Mari holding this. It was made by Lincoln Labs, which is a lab out in Boston associated with MIT. What that chip really is a whole bunch of metal plated. It looks like a bunch of fingers if you were to zoom in. Each one of those is something you apply a voltage to. And then what we do is we ionize atoms, and then we trap them with all those voltages. And I'll show you a picture of that. This trap gets inserted into a 4 Kelvin cryostat. So there's Mari and my other student Will, very nervously, very carefully, taking that very fragile chip and putting it into a socket inside a cryostat. And actually, Mari designed that whole gold-coated thing you see there with all those magnetic field coils. That was all designed by Mari and assembled by her. And then that goes into this 4 Kelvin cryostat. So this can operate at much higher temperatures, but still not at room temperature. And there what you see is a string of 21 atoms. Each one of those is an individual strontium atom that's had one electron yanked off of it. And those are our qubits. And those qubits are encoded in electron states. Like you learn in chemistry, electrons can be in different orbitals. We encode the qubit and the electrons being in different orbitals of that atom. And Quantinuum and IonQ, I see an IonQ t-shirt. IonQ is another company that makes commercial quantum computers that you can access. And actually, IonQ, you can even, both IonQ, IBM, Quantinuum, you can even pay them money, and you can put a quantum computer somewhere on campus, for example. That's something we could do. So those are state-of-the-art qubits, and that's what they look like. Let me ask you, yeah, please. That's an atom called strontium. Yep. It's a particular isotope of strontium. It's strontium-88. And we actually shoot lasers at it. Oh, let me say a few other things. We shoot lasers at it to ionize it. And then the way the quantum circuit runs in this case is we use laser beams to manipulate the quantum states. That's how we run our quantum program. We turn a bunch of laser beams on and off, shooting at those ions. And then the readout is actually we measure fluorescence, and we use a microscope to measure the atoms emitting light. And I'll show you some fluorescence in a minute here. Yeah.
How long can you keep coherence before something causes decoherence?
Yeah, so the question is, how long can you keep coherence before something causes decoherence? One reason atoms are great for this purpose is if you do the hard work, and this has been demonstrated. First of all, we know everything about these atoms, and every atom is the same as, every strontium atom is the same as every other strontium atom. Every superconducting qubit is a unicorn and slightly different than every other one because it's manufactured. Not true here. Seconds. So what's special about atoms is if you do all the hard work, you can keep that quantum state preserved for seconds, minutes even. It's not quite that good, but it's milliseconds or thousandths of a second in the commercial ones, I believe. Yeah.
Is internet a computing process? Why internet is called internet?
Is your question, why is the internet called the internet?
How it works?
So I think that's a great question, but I think that's a little bit separate than what we're talking about today. So let's follow up and talk about why is the internet what it is and why is it called that. That's a very good question. How about another question? Aha. Well, you know, you know, everybody should try to get along and make sure all the qubits want to be with the other qubits. I think that's very important for them working together. It's actually a pretty good question. You can see here in the string of atoms, they're actually repelling each other because they're all charged. So you see that string of atoms are all separated from each other. We're trying to squeeze them all together, but because they're all charged, they repel each other, and they don't quite want to be together, but that's a good thing because it allows us to keep them. We use the fact that they repel each other to be able to see all of them, and so they don't collapse into something. So it's a very good question. Actually, does anybody know what some of the first evidence is that there were atoms in the universe around us? Does anybody know? Light? You're onto something there. In 1814, Fraunhofer looked at the spectrum of the sun. So he took a prism and spread out light from the sun onto a wall. He found a total surprise. He was flabbergasted. He saw dark lines. You see all those dark lines in that spectrum? It looks like Roy G. Biv, right? But there's dark lines, there's colors missing. That was the first sign that there were atoms. And what there was is there were atoms in the outer surface of the sun absorbing light. And atoms only absorb certain colors and certain wavelengths or frequencies of light. And that was the first evidence we had for it. He just didn't know what it was at the time. And actually, I have something here, which is pretty fun, which is a bunch of different atoms inside a tube. And you can see they emit only certain, if I heat them up, they emit only certain colors of light. That's hydrogen. And actually, that's a mix of a few colors, but the primary color there is red. What else have I got here? I wanted to get to neon. Neon glows kind of orange. This is a reverse process. This is a process of the atoms emitting light, but neon will absorb just that color, and that's what's happening in the light from the sun. It took another 100 years for people to figure out and make a model of what those atoms were that were creating those dark lines, turns out. So this is one reason I love being a physicist, is these mysteries all around you that you can contribute to figuring out, and this is how we first knew that there were atoms. Except Fraunhofer didn't know what they were at the time. He just knew they were dark lines. Totally flabbergasted. Okay, that was a side topic, kind of fun. All right, so here's the summary of the state of the art. I just told you about two types of qubits, that they're real machines. There are other ones out there too, other types of technologies. Why haven't quantum computers revolutionized the world yet? A reason they haven't revolutionized the world yet is because you need millions of qubits for practical applications. And there's another technology that has a few thousand using atoms. So we don't have enough qubits. We don't have a big enough quantum computer yet. Also, the qubits we have are still a little bit too noisy, and we can't control them well enough, so we can't run perfect quantum programs on them. And also, we don't even have like the software tools we need. So anyone here who does a little bit of programming in something like Python, where you don't have to know anything about how the computer is made. Like I don't have to know how my laptop is made in order to write a program on it. For a quantum computer, you still have to know everything about all the hardware and about the qubits to write a program. So we don't even have software tools yet. But there are people working on overcoming all these challenges. Something else, which sometimes is, I think it's exciting, so I tell people about it. Even what quantum computers are good for is an open question. So what can quantum computers give us a quantum advantage in? We know one thing, factoring for sure. So that kind of quantum speed up I talked about. We think, and we're pretty sure, it can be used for modeling physics, modeling chemistry. We think it can be used to accelerate machine learning. We think it can be used for optimization problems, like how can Amazon most efficiently get all its packages around the city of Chicago using the least fuel, and not just take right turns. There's probably something better to do there. And so this is a really exciting problem, and for me, it's an exciting thing that we're still learning even what quantum computers are good for. And see, I'm not so worried about that because look at what happened with GPUs. We made them for one thing, for gaming. They're still used for gaming. Turns out people figured out that they were really useful for something else. We just couldn't have imagined the use at the time. So that's all fine, right? I think any new computing technology turns out it's useful for something. And one thing I'm very passionate about is getting quantum computer in the hands of more types of people
to discover more ways to use it. Yes, you have a question. Is there a what? A con, a downside to quantum computing. Is there a downside to quantum computing? Yeah, I mean, that's the application I started with, was that they can decrypt information. And so there's a problem there. We have to change how we securely transmit information. And we know how to do that. Once there's a big enough quantum computer, they could decrypt a whole bunch of information. That's a kind of downside, I think. Yes?
What about electric power consumption of these quantum computers? Are they like substantially higher than supercomputers, classical supercomputers?
So great question about power consumption. We believe that you can reduce power consumption and do some things like machine learning. There's some evidence now you can do machine learning, you can reduce the power consumption of machine learning. This is really important. We're on a trajectory in the world right now where we want more and more machine learning, and we're going to outpace the amount of energy that we have to run it. In fact, Microsoft is turning back on a nuclear reactor to be able to, 3 Mile Island nuclear reactor, to be able to do more machine learning because they don't have enough power, baseline power, right? So we think quantum computing can reduce that energy. Maybe even if it can't do it faster, but it can reduce the energy needed by 1,000-fold, that would be a big deal. And there's some evidence that that this is true. Okay, I'm going to take a couple questions. I want to show you one more thing. Stay on time. Okay, in the back and then up here. Yeah.
Mentioned noise several times. Are there any physical or other methods that are used or potentially be used to reduce that noise?
Yes. So part of what it is to be a quantum engineer or quantum physicist is to try to figure out ways to reduce noise. I'm going to come back to that and tell you one thing that we're thinking about to reduce noise. Let me come back to that. Take a look at this picture right here. This cryostat, at the very top of it there's a motor. That motor introduces noise. I'm going to tell you about a big project in the state and a $500 million investment to be able to do quantum computing without those motors on top of that thing. Okay, so these are the challenges right now. And we're in it's a global challenge to overcome all of these issues and achieve what we call quantum utility, where it actually is useful for something. It can actually reduce energy usage of computing, or it can actually accelerate some computing task. So there's a global challenge right there, and every country wants to be first to do this. So let me just end on something exciting I've been so excited to be a part of, which is what the state of Illinois is doing to try to accelerate this and to bring more jobs and more industries to the state. I'm going to skip some of this. And the state, our state of Illinois has done something incredible, which is to form what we call the Illinois Quantum and Microelectronics Park. It's actually a company now. As Irene mentioned, I'm the chief technology officer of this company. This company is a company to make a 130-acre park south of Chicago. And this picture at the top, you can see downtown Chicago and where we're going to make this park. You can see one of the anchor tenants at this park is PsiQuantum. It's a company that uses yet another kind of technology, or photons or particles of light as their qubits. They're an anchor tenant there. And that's the former US Steel site, actually, that went out of business in about 1992. And now we're very excited to bring to that part of Chicago the next generation technology, next generation industry there. So this is a rendering. This isn't what there is today. What there is today is park, and we're going to preserve the park, the Steelworkers Park, as we build this. But that's the idea, is we're going to build this. And we're going to do something incredible there I'm going to mention in a minute. So this is really a first of its kind campus for quantum computing and to put the infrastructure in for advanced microelectronics and quantum computing R&D. The team is awesome. It's an all-of-state team. You'll recognize some folks on this team. Our governor and his staff, like Claire Lindbergh and Kaz Peters, who works for the Department of Commerce and Economic Opportunity. John and Prudy, who work for Intersect Illinois, which is another economic development agency in the state, are part of that team. And then the University of Illinois is leading this. We are the IQMP. My neighbor and colleague, Harley Johnson, who's a professor of mechanical engineering, is our CEO. Some of you might recognize Laura Appenzeller. She's the director of the Research Park and Enterprise Works in town. She's our chief operating officer, and I get to be the CTO, which has just been great. And then everybody's participating. All the national labs, all the universities are all working together to try to pull this off. I mentioned it's on this 130-acre park south of the city, which is a former U.S. Steel Southworks site. And I can't remember why I put this slide there. But anyways, $500 million investment in fiscal year 25 to build it out and to build a giant cryo plant. Okay, so to this question, how are we overcoming noise? We're gonna put a giant plant there that'll circulate ultra cold helium and allow us to have all these cryostats for quantum computing without the motor on top of it, which will be much more efficient and remove a whole big source of noise. We're also recruiting all kinds of companies. The governor's point of view on this investment is that it's to build jobs in the state. We've got about 30 companies in a pipeline right now that we're trying to bring to the state. The first was PsiQuantum. There's another one we'll make an announcement soon. And I was visiting with a company from France up in the city this last week, that wants to move and create jobs and opportunities in quantum computing in the state. So it's really exciting. And there's going to be all kinds of companies there, from startups to Fortune 100 companies will be located there. PsiQuantum is a startup. It's a very well capitalized startup. But soon, I think we'll announce soon some companies you may have heard of before that will be there and trying to push forward and get, for the first time, to the point where quantum computers are useful. So that's a big thing that's happening right now in the state. You'll hear more and more about it over time. And I'm so excited because I think it's, the state, it'll be great to have a high-tech sector in the state. I've had many students from my research group who get their PhDs and go off to the coasts to work in these very exciting industries. And with this, we'll have all kinds of exciting jobs in the state for our awesome, talented students to stick around. And that's that. Yeah.
That article that I read talked to you about what makes a bad quantum computer makes a good quantum detector.
Yeah.
Could you elaborate on that? They
So-
mentioned possibly using it to look for dark matter.
Yes. So the question is, you've heard something about a bad quantum computer being a good quantum sensor. What is that all about? Well, you remember how I told you that qubits are really fragile? What I actually mean about that is, okay, let's say I have a qubit and I said it could be 0 and 1 at the same time, which means it points horizontally on the sphere. Nature, all that noise, what it's trying to do is, it's like nature really doesn't want it to be in a superposition, 1 and 0 at the same time. Nature's always like, cut it out, qubit, cut it out, get over to 0 or get over to 1. Stop doing this superposition thing. So that's what noise is doing it all the time. If that noise is something you want to measure, that sensitivity to noise becomes a feature rather than a bug, because it means that noise very sensitively can flip the qubit to be 0 or 1, and you can detect that and make a sensor out of it. And you can make really great sensors out of that particular feature. That one on the right there, that's a prototype of a sensor which allows you to measure acceleration and rotation without drift. So what am I talking about? So last year, at the end of the year, I went onto an aircraft carrier out to sea. It was awesome. The USS George Washington, spent a night on it. I was out on the tail of the ship, and I was talking to the captain. I was like, what's hard here, right? He's like, Brian, if we end up in a conflict and GPS gets denied to us, we have a problem navigating. We have a backup system. The backup system is something that can measure how we accelerate and how we turn. But it drifts. The gyro drifts in time. And every once in a while, I got to turn the boat in 360 degrees to recalibrate the gyro. In the middle of a conflict, this doesn't seem like such a great idea, right? That's what we have now. So this kind of device, could you put it on a ship? It doesn't have that drift. And in a GPS-denied environment, the captain could navigate without having to do things like stop and turn the boat 360 degrees. And it happens to be the properties of the qubits are what allows that to work. So that's why bad quantum computers make good sensors, is that sensitivity to noise. If the noise is something you want to measure, like gravity or like rotation, then it's really useful. Yeah?
Are qubits
That is an awesome question. The question is, do we have to, so the qubit can be anywhere in 0 or 1, point on a sphere, and then we read it out. We read, at the end, you read something out, it's 0 or 1 at the end of the computation. Could you worry about it pointing over here? Yeah. So there are types of quantum computers that actually do something more complicated and read out like other properties of the qubit to try to do computation in a different way. So that's a really good question, and people are working on that right now. There are things called like bosonic qubit codes where it's a different encoding of the quantum information, and people believe that can make it more robust against this noise and certain kinds of noise. So yeah, you can do that, and people are working on that. That's a great question. Yes? Yeah. Great question. So I mentioned PsiQuantum is working on computing using particles of light. And actually what they do is they use photons that are particles of light, and they actually make circuits out of them because you can guide photons. Actually, I have an example of that here. So I'm going to turn out the lights, so just watch yourselves for a minute. So this is what's called a waveguide. It's a piece of glass, and I can shoot light in one way, and it's guided all the way through that glass to you, to the other end. And I can miniaturize that and make a circuit out of it to have switches and all kinds of things that allow you to manipulate light like an electronic signal. It's different than an optical computer. There are people who try to make regular computers out of light using those circuits, but those are still, the light is 0 or 1, and it's not single particles of light. So it's different in that they're using single particles of light, and they can be in the superposition state and this superposition and entangled. So it's different than optical computing. How about in the back?
When you say superconductors have 0 resistance, is that like they have like not negligible resistance, or is it actually like there's no?
Okay, so the question is superconductors, people say there's 0 resistance. Is it really 0? It's not really 0 for really beautiful physics reasons. It's just very, 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 very close to 0. Yes. It's closer to 0 than you could ever make in a metal. It's like 1 billion times or 1 trillion times lower resistance than copper. It's not exactly 0, though. Very close. And if a physicist ever tell you it's 0, it's not really 0. It's just very close to 0. Yeah. Yeah, 0. I mean, to like have something actually be 0, that's not a thing really in nature. It's really, 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 really tiny. Yeah.
Are there then devices that are sensitive enough to, for example, allow you to measure power losses on a superconductor? Can you measure it? I mean, you're saying that resistance is not exactly 0. So could you measure losses on a superconductor?
Yeah, you can measure losses on a superconductor. It turns out, and we have folks around here who do that. So my colleague Alexei Bezradian, who's in physics, actually measures that kind of thing. So if you have a really big chunk of superconductor, that non-zero resistance gets really, 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 but it's really, really tiny. It's hard to measure. But if you make a tiny little itsy bitsy superconductor, you can start to measure it. Yeah. Sorry, I skipped over. Do you have a question? And then I'll get you. All right.
You talked about the 4 different designs of quantum computers. So is there a reason why some are better than the others? So like IBM and UIUC is using superconductor design instead of like the photon?
Yeah, so let me go find that slide really quick. Okay. And actually, we're in the state and here, we're working on all of these, actually. So what are the great question, what are the trade-offs? So here are some trade-offs. Atoms, like I mentioned, so I work with strontium plus atoms. Anytime I trap a strontium plus atom, it's the same as every other one in the universe because the strontium atoms are all identical. Turns out this is true in the universe, just like every electron is identical to another electron. So that's a really great thing because when I make a quantum computer out of atoms, I know exactly what colors of light, for example, I have to use to run my quantum program, what lasers I have to buy. I don't have to tune it up. However, with atoms, that's the upside. The downside with atoms is I got to figure out how to get a lot of lasers all turning on and off at the same time. It's a really hard engineering problem that is hard. And we haven't really figured out yet how to get it to a big enough scale to make it useful. Okay. Let me use another example, which is the superconducting circuits. Every time I make a superconducting qubit, and I showed you an actual qubit, a micrograph or a picture of one, every time I make one, it's slightly different than every other one. And it changes over time a little bit because it ages. So that IBM quantum computer, a big challenge in that thing, the 433 qubits, is it has to be constantly tuned up, and you have to constantly figure out what's exactly the right electrical signal to send to the qubits to run your program. That's the downside. The upside is I can fabricate on a big wafer a lot of qubits and run it through a fab and fabricate it because it's manufacturable, which atoms are not exactly manufacturable in that way. So all these things, we're exactly in a scenario where like every one of these has some upsides and some downsides, and actually we don't really know the whole engineering pathway forward to figuring that all out. And actually I mentioned at the end there was something on the slide. Another thing the state of Illinois is doing is we've made a partnership with the Defense Advanced Research Projects Agency, or DARPA. It's the Illinois DARPA Quantum Proving Ground. It's going to happen at that park, and it's part of a program to try to accelerate and get to, in the next 5 years, a prototype quantum computer which is big enough where we have all the engineering answers, and if we could move it forward and pour enough money on it, we can make a big one. So that's a project which is going to be happening here in the state of Illinois. It's been called, not by me, it's been called by the governor. I've heard him call it this kind of Manhattan Project, but for quantum computing. Try to get there as fast as we can. So that's another awesome thing and another full-time job I seem to have acquired. Yeah.
So my question is about how you're storing the information to the photon. Is this like checking the polarity of the photons, or is it more about like the exact position or energy level?
There's a lot of ways to store information in a photon. It's a really good question because if you know some physics, it starts to be like, how are you going to do that? There's different ways to do it. One way is in the polarization of the photon. So you may know that photons are really, or light is an electromagnetic wave, and it has an electric field that's waving, and has a direction that it's waving or oscillating. And so you can encode the quantum information in, let's say, it's waving horizontally or waving vertically. It's a little even weirder, and sometimes even though I'm working on this, it sometimes bothers me. You can also store it in when the photon comes. So you can make bins of time and say the photon comes now or later, and it can be in a superposition of now and later. That should bother you. It bothers me, but it works, turns out.
Like based on when your thing's emitting the photon.
You got it, yeah. When the photon emitter emits it. And it turns out you can use time bins also to encode the quantum information. Lots of ways to do it. That's kind of weird. That should totally bother you. Yeah.
So in order to do this, you need single photon emitters.
Yes.
How do you make a single photon emitter?
Turns out on here are some really excellent single photon emitters. Atoms are really great single photon emitters, so that's one way to get photons out. Defect centers and crystals are good photon emitters. You can also make good photon emitters basically, I would say materials are one way to do it too. You can shine multiple laser beams on certain kinds of materials, and in certain circumstances get single photons out. And people are working on making that better. Atoms are basically the best ones, but again, it's not like it's not very manufacturable. So atoms are the best single photon emitters. And then people are trying to make defects, color centers, and crystals and other things really good photon emitters too. So that's also a big challenge right now, is making really good single photon emitters. That's one thing PsiQuantum's got to figure out. Yeah.
For something like a single photon, your detection for that has to be like in like every dimension, like every direction, right?
Everyone here has a really good question. So this question is about, hey, hold on a second. If I have an atom and I'm going to use it to emit light and be a single photon emitter, doesn't that light go everywhere? Isn't that a problem? Yep, that's a huge problem. So people are trying to figure out how to get the light from atoms to all go in one direction. And from defect centers, same thing. That's a big, and there's people here over in the Holonac Micro Nanotechnology Lab who are learning how to integrate some of these single photon emitters into waveguides that are made to direct the light in one direction. And there's some very clever people working on that. Yeah.
Why use that particular ion of strontium as compared to another element?
Yes, in fact, people use, okay, so the question is, why the heck am I using strontium-88 plus? There are some of these different companies like Quantium and Quantium and IonQ use different atoms. Why do people choose these different atoms? The atoms, nature has, the way nature works is these atoms have different properties. They have different energy levels in them, or orbitals that need different wavelengths or colors to control them. My group chose strontium because I can buy all those lasers and they're very turnkey. And it will do everything I want it to do. So great. You would not use strontium to make a large-scale quantum computer, and I'm not trying to. Other companies like IonQ are starting to move into a particular isotope of barium, which is another atom, which maybe has the right properties to be able to get to a very large-scale computer. So for me, it's just a practical matter. I could buy all the lasers. They're very turnkey. We need lasers from blue all the way to infrared, but I can buy them. They work great, and it does everything we want. There you go.
Don't mind, I'd like to wrap up with one
Okay.
question. If I was a student thinking about wanting to get into quantum computing and joining this new microelectronics, quantum and microelectronics park, what might I want to study in school?
Great question. What can you study? This is something that's changing. 10 years ago, I would say, go study physics, because basically all the quantum engineers are really physicists, mostly PhDs. This is changing very rapidly now, where these quantum companies, these quantum computing companies, they still need some physicists, but a great example, the French company I was meeting with this week up in Chicago, we were like, what's your hiring needs? It was like, we need electrical engineers, we need mechanical engineers, we need computer scientists. So now if you want to get into this industry, there are many different degrees and routes forward that you could use as a student to get into it. And so I think physics is good. They definitely need computer scientists, definitely need electrical engineers, definitely need mechanical engineers. Some need for materials scientists, some need for chemistry. Yeah. So a lot of the physical sciences and engineering are a good route in. Okay. Well, thanks for all your questions. It was really fun to talk with you today.
Thank you all.